Okay, so now you are a computer scientist. Because you know how to count sequences in a set. You know about information theory. So what you have to remember is that there was a guy, his name was Claude Shannon, who wrote a paper in 1948, and he found all this very nice. He founded a new field giving the fundamental results of communication. So, I mean, now that you have seen some of these results, I think you can appreciate how strong this theory is, because there are very few fields where you know what the grade is, what is the bounds, what you can achieve. So this is something very special, and information theory delivers this kind of message. So we know how to perform optimally lossless compression. We've been to lossy compression, so the main motivation was to be able to compress. So why do we want to compress with losses, in particular if we have images and video? Because the rate that videos are delivered, it is a huge, it represents huge data. There is no other ways to deliver them if we don't make it with losses. So there are fields where we don't want to have losses. For instance, for medical images, I mean, here you want really to do lossless compression. You would like to retrieve exactly the data. In satellite also, I mean, having satellite images cost a lot. So that's a field also where we don't want to lose something. So we have almost lossless compression in these cases. But in all other cases, we go to lossy. So we've just seen the theoretical results. So there is a trade-off between, when we do lossy compression, there is a trade-off between quality and rate. And now we would like to see how to implement it, okay? And the way it is done in image and video compression, it is made with uniform scalar quantization and entropy coding. So entropy coding, you know. And now we'll see what it means to do uniform scalar quantization. Okay, so what is quantization and scalar quantization? So scalar means that you take one symbol, and that can be real, and you will represent it with fewer levels, okay? Okay, and so it's a symbol by symbol function, and the function, the quantizer function is shown here. So on the x-axis, you have the input, so it can be a real, for instance. And the output, it is on the y-axis. And here you see that for the representation, so after quantization, you will have only a few levels. So they are denoted by this x hat, okay? And you read it that way. So if you have an input that is, for instance, between uk minus 2 and uk minus 1, it will be represented by x hat k minus 2, okay? And so you see this is a scalar quantizer. And you could also do a vector quantizer. I mean, you could have at the input a vector and then have one reconstruction level per vector. Okay. Okay, so, and we say that the scalar quantizer is uniform when all the steps have exactly the same length. Okay. So, what is the effect on of the quantizer on the distribution? So imagine that your input distribution here is in black. The fact that you quantize the data, what you will have at the output is this discrete distribution. And this value is, in fact, the area under this curve. Okay, and here, this value, this is this area, etc. Okay, well, it's simple, right? Yeah. Why is it good? Ta-da! Nice result. A new theorem. So what does this theorem say is that, okay, look, the encoder is very specific. So you do this scalar quantizer. I just explained in the previous slide. Then after that, you do the entropy coding that we have seen. For instance, Huffman coding. Then you will have a distortion. The distortion, you can measure it between the input and the output of the quantizer, but it will be exactly the same as the distortion between X and this one. Why that? Why is the distortion that you see here is the same as the distortion that you would compute between here and here? Because it is lossless. Yes, it is lossless. Okay. So all what you do here is just compressing, but you don't introduce more losses. Okay, and then you have this nice theorem, so we'll go to it. First, I will just say a few words about all these references. As you can notice, there are different references. So because they have been reinvented in different countries, so you can look also at the time. So it was also a time where there was no much communication between Russia and the States. So this was developed in Russia. And this was developed in the States, but this was developed in Bell Labs. And the only publication that was done here, it was an internal publication. And so it was reproved a few years later by Gish and Pierce. Okay, well, now that was just a history. And what does it say? It says that whatever the density is, this solution is optimal up to a small gap that I can compute in terms of distortion. So I can compute it in decibel in logarithm. So I don't compute the distortion, but rather the signal-to-noise ratio. Bon. And this is a gap. Or I can compute it also on the number of extra bits that I will pay for that. And the number of extra bits, it's only 0.26 bits per symbol. It's nothing. It is nothing. But what is strong in this theorem, it is that it is for all densities. Whatever the data you have, if you do that, you only pay that. So we'll go for that. Because the complexity of such an algorithm, it's only linear in the length of the data that you compute, okay, that you process. Okay, I just, and in fact, it is because of this result that uniform scalar quantizer plus entropy coding is extensively used in video coding. Okay, so just to have a curve. It's nice sometimes to see curves. So here we represent the distortion versus the rate. So, but I represent it in the more classical way of representing the distortion. So it's not a distortion, but it's the inverse of the distortion, and we take the logarithm. So this is this signal-to-noise ratio. So you know this criterion. And here in black you see the optimal curve. Okay, so not exactly the optimal, but the one from Shannon. And here you see that if you use a uniform scalar quantizer plus variable length code or an entropy coder, you will get this dash curve in red. And Gish and Pierce, they also computed this gap when the length, so for high rate, well, anyway. But here you see, so what it means to have 0.526 bits per symbol is just that you shift the curve here by this value. Okay. Bon. So we have a nice way to do. We don't lose much. But then you can say, oh, I would like to do it better. I would like to do better. Okay. So let's try to do better. What is the loss due to? So if you look at the quantization cell shape that you get for scalar quantizer, it will always be of this kind. So what does it mean here? So have two axes. So imagine that you would like to compress a vector, so two symbols together. Okay, the x-axis will be one dimension, and the second dimension will be the y-axis. Okay, with scalar quantizer, what happens is that for each dimension, so for each dimension, if you have two, so here in yellow, you have all the possible samples, okay? And all the possible samples in a cell, in a square, they will be mapped onto the blue cross, okay? And this is the way you quantize the data, okay? All the data within a cell, they will be mapped onto the centers. It is a centroid, and for a scalar quantizer, since you do it dimension per dimension, you will get this kind of shape. What you could do is to find another way to, in a more optimal way, to do vector quantization, such that to find new cells, okay? And if you optimize your vector quantizer, what you will get for a uniform distribution, you will get this kind of shape, okay? And if you go for a Gaussian distribution, you will get this kind of shape. And this you cannot achieve with scalar quantizer. Scalar quantizer, the cells will only have boundaries that are aligned with the axis, okay? So the only way to do better is to go to vector quantization. You know this algorithm. Of course you know. So what is this kind of algorithm? In order to find the best, so you have to map, so the definition of such a cell is that this point here is closer to this point than to any other. Clustering, very good. It's a k-means. I mean, it's a very classical algorithm that you find here again. So there is a subtlety, because in k-means, the only criterion that you take into account is the distance. Here it has to be optimal for our problem, that is rate and distortion. So here we do a clustering or a k-means with a loss that takes into account not only the distortion, but also the loss. Okay. But that's the same way to implement. Okay. And now you understand why you don't want to go to that. It's because of the complexity. Even if you know already this mapping, the way you implement, you do the encoding, it will be, the complexity will scale with the number of data that you want to process, but also with the number of centroids. And the problem is that the centroid, the number of centroids will grow exponentially with the dimension, so with n. So you don't want to go to that, okay? Okay, so you believe me, we want to be linear. If you want to look at your images and videos real time, if you don't want to download it and come 100 hours later and to be able to watch it, we have to go to linear. So we will forget, we will pay a little bit more in terms of rate, but we will have a linear complexity. Okay. So you know how to do it. You know how to do so lossy compression, uniform, and entropy coding. Now let's look at the true life. We are getting closer and closer to real life. We would like to take into account memory. Okay. So for that, I will first get some I will manipulate, I will do some math on entropy and the meaning of entropy in order to get the intuition. So the whole intuition about transform coding and the way we exploit memory is in this formula. So what does it mean? So if I compute the entropy of a vector, and if I apply an invertible function, I don't modify the entropy, because the entropy measures the amount of information that I have in data. If I apply an invertible message, an invertible function, then I have not modified my message. I mean, there is still exactly the same amount of information. So the entropy is equal. I mean, if I apply this f, the two entropy are equal. And now we can show that the entropy of a vector is the sum of the individual entropy if and only if these variables are independent. So if I find, and so if from a, so here you have to believe me, but it makes sense, right? If my data have memory, I have to compress them together, right? And if they are not, they are independent, I can compress them separately. It's what it says, okay? And, yeah, this is the operational interpretation of this formula, okay? If here, if I have to deal with vectors here, and here I can go scalar symbol by symbol, okay? Well, so, but for that I need to find a function that is invertible. Okay, but if I cannot achieve pure independence, but only uncorrelation, if I can only decorrelate my data, meaning I can only remove the linear dependency, then in that case, if I compress it with a scalar symbol by symbol, the rate will be a little bit higher, so we'll have something to pay, but I hope that it will be more or less close to what I had before. Okay. So, well, let's go for that. Let's try to find a way, a function that can decorrelate my data. So, decorrelation, it's linear, removing the linear dependency. In other words, it's applying a linear transform such that my data will be almost decorrelated. So I write again. So my goal, here what I want to find is a matrix such that my uniform scalar quantization is quasi-optimal. So the way that I used in order to do Lotti compression. So in other words, I would like to find the matrix A such that when I apply it to my data are decorrelated. Okay? And this will be the way I process. So I will have a vector of data, apply the forward transform, then I can do scalar quantization, so one per dimension, okay, and then I can do the entropy coding, and the decoder is done. It's just the reverse, okay. Here I introduce just a few words because what is called encoding and decoding in information theory, in signal processing, it's called analysis and synthesis, right? So nothing with what Yannick presented us, but that's the way we, well, that's just a question of vocabulary. And it makes sense in a way. You make an analysis, so you analyze your data, you find a new representation so that you can better analyze your data. And when you do here the decoding, what you want is to retrieve your data. You want to synthesize your data. Well, and another vocabulary that I may use is that the use after the transform, most of the time we call them coefficients. Okay, so now that's the time where we do a little bit of linear algebra, right? Okay, so let's go for linear algebra. Okay, so I rewrite the problems that we want to solve. We would like to find a matrix such that the covariance matrix after the transform is diagonal. In other words, I would like to diagonalize a covariance matrix. And how do we do that? Well, how can we diagonalize a matrix? Well, it's written, yeah. Eigenvalues, eigenbasis, yeah, correct. We have to find an eigenbasis of the covariance matrix of the data that we want to process. Okay. Well, but not, we have to remember, I mean, our course in linear algebra, not all matrices can be diagonalized. Yeah, some of them can. But which one? The symmetric matrices. So here it's a crash course in linear algebra. When you do signal processing, the only thing that you have to remember about linear algebra is that symmetric matrices, you can diagonalize them. And moreover, you can diagonalize them over R, over the reals. The eigenvalues are reals. And moreover, the eigenvalue, the eigenbasis is orthogonal. Oh, that's nice. That's nice when you do processing, because when so what does it mean? It means that the matrix of the eigenbasis is orthogonal, and it means that what it means is it is orthogonal. It means that the inverse is a transform. And that's nice. Why is it nice? It's because you don't need to compute the inverse. Or the inverse is very easy to compute. You only have to transpose. your matrix. And that's something that we like. Okay, so the optimal is called the Karinahan-Love transform. Okay, so the matrix that we will apply is just the eigenvectors that we put in line. Okay, and if you do that, what you will obtain is that the coefficients are indeed decorrelated, and that the new covariance matrix of the covariance matrix of the coefficient is indeed diagonal. So just to note, I mean, this transform has many names. It is also called the principal component analysis, so that's maybe something that you've seen also. Well, it has been reviewed and reinvented in many fields. Okay, so it can be seen with different names. Okay, so there is subtleties about the differences, but I think we don't need it for today. Okay, so now, okay, so this transform is optimal to decorrelate. But what we want to do is compression. So is this function, this matrix as decorrelate also optimal in terms of rate distortion? And the answer is yes. So you see it's a much more recent result due to Goyal. And it says that if I do scalar quantization and I apply a transform coding that is indeed, so or if I look for the transform that is optimal, in terms of rate distortion, and it will be this Karinahan-Love transform, so the transforms that can indeed decorrelate. So I take here an example. So I take something called a Gauss-Markov model of memory 1. So it means that it is I introduce memory, but memory with a window of 1. So one symbol Sn is the previous symbol Sn minus 1, and then I add some noise, and this noise will be Gaussian. And in order to be able to have a degree of freedom on the correlation levels that I have, this will be done with this rho. So here I take an example where the correlation is quite high, so the correlation level can go from 0 to 1. Okay, okay, and so here I plot again the distortion versus the rate. Okay, so it's not exactly the distortion, but the inverse of the distortion. Therefore, the lower bound is no more. It's not the lower bound; it's an upper bound because I look at the inverse. So okay, so this is the Shannon lower bound, and here in red there is the optimal function, distortion rate function. And now I will look at some implementation. So Karinahan-Love transform followed by scalar quantization, etc. And here what you see is the performance that we can achieve with this Karinahan-Love transform. And when the dimension of the matrix goes to infinity, okay, I see that the performance will get closer to the bound, to the optimal performance, and that the gap is again this 1.53 decibel. In other words, it means that this transform is okay, is optimal, okay, in this context, okay, and again, the only gain or the only loss that I will have with respect to the bound will be again this exactly the same value, okay, or this 0.26 bits per symbol. And this is the reason why, okay, transform coding is used, because again, with linear, almost linear complexity, and we will go into that, we can achieve something that is almost optimal. Okay, so let's have a look at some pictures. Okay, so here I represent some cloud, point cloud of data in the 2D space. Okay, so I create Gaussian data that has memory. Data are correlated, and so you see one blue dot represents one sample. Okay, So, and in the first figure, this is my original data, and the data are correlated. You see that there is a trend that when x0 increases, x1 also increases. So there is a trend in the distribution. So they are correlated. And if we apply this optimal decorrelating function, what happens? So, so you see that you rotate. So thanks to the transform, you rotate your data, and what you achieve is this new point clouds. And here you see that when you increase u0, you can, there is no more this trend. Huh? So there is no more this trend that u1 will increase as well. So you have decorrelated your data. Okay. So this is the effect of this transform. So there is another way to look at the transform, and this is a classical way, in fact, to present. Usually when you get into a course on image and video compression, they tell you, oh, you have to do the transform because it can do energy compaction. So well, I prefer to present it the other way around, to tell you that it is optimal up to a small loss in terms of compression, and then we'll go to this intuition that this transform can do indeed energy compaction. So there are two ways to look at that. You can look at the covariance matrix. So before transform, your covariance matrix is full, okay? So it is given by this value, and when you apply the transform, you get this one. So it is decorrelated, so it means that you have a 0 here, but you can observe here that the variance of the first coefficient is higher than here. It was 1, and then it goes to 1 plus rho. And of course, you haven't created the transform is orthogonal, so you don't increase the energy, the whole energy, and the second, the variance of the second coefficient is reduced. Okay, you can look at the same thing here, also with which is more a geometrical interpretation. So if you look at so this is the distributions that you have, and if you do direct encoding on this value, so it means that you will have these quantization cells, okay, that will be aligned with the axis, okay, and then you see that here the variance that you will have on one dimension or on the y-axis is quite high. But if you apply now the quantization in the transform domain, so after having rotating all your data, what you observe is that the variance that you have here is much smaller on this direction than in this direction. Okay. Okay, so, and in fact, we can show the optimality of this energy compaction. I mean, the way, so indeed, applying this Karel-Love transform is optimal in terms of rate distortion, but it is also optimal in terms of energy compaction. So this is what I will show now. And in order to do that, we look at another problem that is dimensionality reduction. So this is a problem that we all face. We always have data to handle that have a high dimension, and we always ask what is the best way to represent them with a smaller dimension. I mean, in all fields, that's something that we have encountered, and I'm pretty sure that you had this problem before. So here I look at dimensionality reduction, but that is linear, and I would like to optimize the matrices that perform the best linear dimensionality reduction. So how it is, so at the input I have a vector of dimension n, and I apply a matrix that will, then I will have a vector of smaller lengths, and then we have another matrix in order to go back to the original domain, okay? So I will lose data for sure, I mean, I lost some dimension. But I would like to find the best approximation. Okay, and so I would like to find these things. So I would like to find the best matrices. I will minimize over all matrices the distance between the input vector and the output vector after the dimensionality reduction. Okay, and if you solve that, wow, that's magic. What you will find again, this is the Karinahan-Love transform. Again, I find the eigenbases of the covariance matrix of the input vector. Okay, so it means that this Karinahan-Love transform that is optimal for the compression problem is also optimal for dimensionality reduction. And I can see that, okay. So this Karinahan-Love transform compacts the energy the most, and I can see this. Okay, here, what do I plot? I plot the number, so here on this axis, this is the number of coefficients, so after transforms that I keep, and I look at the percentage of energy that I have in my data. Okay, if there is no transform, it is just linear. But if I apply the Karinahan-Love transform, I have put much energy on the first coefficients, okay? And therefore, the curve that I get is the following. So this is the energy that I get if I keep on me this amount, so 5% of my data. And if I don't do any transform, then I will get this. Well, it might be a little bit, yeah. Well, we'll see. So I will now make a summary on this Karinahan-Love transform. So what you have to remember is that the Karinahan-Love transform is, it is an orthogonal transform, so we like that because the inverse is easy to compute and it can decorrelate the data. We've seen that it is, it helps to decorrelate, that's the most important thing. But so, well, the Karinahan-Love transform, you compute it based on the covariance matrix of the input vector. So it means that it depends on the signal. But so it's not good when you do compression, because it means that when you want to compress your data, you have to send also the transform. It will cost. So that's not good. But it's not bit rate dependent, which means that whatever the rate, it will always be the same matrix. So you only need to send one, right? And, and there is some optimality in terms of rate distortion performance, in particular for Gaussian sources. Okay. Well, and we can even look at the loss, and the loss is always the same, and it is so the world is beautiful. Let's do a transform. But which transform? Because in fact, this KLT has some problem. The fact that it depends on the signal is not good, because it means that you have to send the matrix. So can we find another transform that does not depend on the data? And if we could find something that is of low complexity, that would be even better. Low complexity to compute. So do you have some guesses? DCT. Transform, Fourier transform, etc. Yes, we'll try. So there is one transform that we like a lot when we do signal processing, is a Fourier transform, because there is a fast algorithm, there is a fast Fourier transform. And so you know, when you make the computation, you multiply a matrix by a vector, the complexity is. So it depends on the size of the. So all this, imagine here I have a vector of dimension n, okay? So here I have an n by n matrix. So if you apply such a matrix, how many operations do you need to do? N by n, n square. Well, it's too much, huh? For you forget again about your real-time video, it won't do the job. But if this matrix is a Fourier matrix, then it will be only n log t, n log n. So the fast Fourier transform is n log n. It's much better, much, much better. Bon, it exists, but is it good? Is it good for our problem of image and video compression? This is what we will see now. So, well, it's not exactly the Fourier transform, because Fourier transform you have imaginary, you have complex, so, and moreover it's over continuous time. So we need first something that is discrete, okay? and we would like something that is real. So there are different ways to do it. There is a discrete sine transform, discrete cosine transform. Anyway, so the one that is used is a discrete cosine transform, and it has a special form. It represents a case. So you know when you discretize, and it means that you have to periodize your signal, etc. So you remember this kind of. Well, in any case, we take one where the way to periodize is make with a mirror signal. So, well, it's a special form, but anyway, the main idea is that it looks like Fourier transform, right? And then you have a wonderful theorem that tells you if you have a Gauss-Markov source, then the kernel of the transform approaches this DCT transform. Okay, so it means that it is near to optimal. Okay, and so before we had something that has the kernel of transform is signal dependent, so you have to send the data all over, it's very complex. This one, the DCT, you don't have to send the coefficients of the matrix because it will always be the same, and it is nearly optimal. Well, you see that, well, okay, so you may see, okay, before we had very strong results for any kind of densities. Here it's less general, but still, well, it's less general in the sense that we have Gaussian sources, but it's nearly optimal. Okay, so I would like to show you the effect of energy compaction with the DCT transform. So I would like to introduce to you Katalin Marton. Katalin Marton is, she got the Shannon Award in 2013. She's also the only woman who has a Shannon Award, okay? Well, and then we will process Katalin Marton. So here you see Katalin Marton, full resolution. And here this is the image of the coefficients that you have once you apply the discrete cosine transform, the DCT. Okay, and what you see, so when it is black, it means that the coefficient is very low. So already what you can notice, this is this property that we have seen of energy compaction. There are just a few samples that are that have non-negligible values. Okay. So it gives you some. So we would like to compact the data. So maybe we could say, oh, I will not keep all the coefficients here, since they are almost all equal to 0. Why not keeping just a few, only 6%? Well, you still recognize Katalin Marton, right? And if now I take 1%, you still recognize Katalin Marton, right? And if I take now only 0.4%, well, Katalin Marton is a little bit fuzzy, but you still recognize her. Okay. Then you could tell me, yeah, but I could have done that directly on the image. Okay, let's do it. Okay, so here I keep only 0.4% of the coefficients in the Fourier domain, and then come back to the image. And here I do the same thing with the pixel. Which one do you prefer? Okay, yeah, it's clear. So this property of energy compaction is something that is very important in this area. Okay, so, so you know now how to do compression, you know how to do lossy compression, and you know how to perform also, to deal with memory. Well, there is another way to do it. It is prediction, and I will do it fast. I will only give you the main result because, in fact, it is very close to. It is very close. So the type of results that we get for predictive coding is very close to transform coding. So here is a summary of what we have seen before. That if you want to perform lossy compression, and this is really a very strong result, is that the distance to optimal, whatever the density is, whatever the distortion is, it's always constant. So if your distortion now is a L2 norm, mean square error, then you can compute it, and it is only 0.26 bits per sample. Okay. Now, if you do transform coding, you get the same kind of result, well, but it's a little bit weaker in the sense that we cannot prove it for any kind of density. We can only prove it for Gaussian and also for this distortion, but people believe that it is true for any kind of distortion. It's just that we can't prove it. Prediction is another tool in order to perform and to deal with memory in the data. You predict from the previous, and then you just send the difference. But anyway, you see that you get exactly the same flavor of result. Okay, and okay, so this is well, and I think now is the time for me to summarize all the results on data compression before we go to DNA-based data storage. That scalar quantization, uniform scalar quantization is really the good tool because it is close to the optimal, and moreover, you know how far you are from the optimal. In order to exploit the distribution, I mean, you know what we did at the very beginning with this intuition that there are some frequencies, that there are letters that are more frequent than others. This is fully exploited by entropy coding and with a complexity that grows only linearly with the data. To exploit linear dependency, then you can do it either with a transform or a prediction. Transform, you will pay, you have a quadratic complexity in the size of your data. Prediction, it's a little bit less, it's only linear. And but the practical way that we implement things is with a DCT, and where the complexity will only be n log n. And that's the reason why we do this in image and video. And now you can tell me, yeah, but this I don't understand. You have prediction, you have transform, why you do both? Okay, in fact, in image and video coding, what is done is that you split your images in blocks. And then inside the block, you use the transform. So you remove the redundancy within a block through the transform. And the prediction is used to remove the redundancy between blocks. Okay. And, okay, you could say, oh, yeah, but you have only decorrelated your data. It's only linear dependencies. What can you do if you want to be beyond and remove all the dependencies that you have in the data? Then there are other ways to do it. There is another algorithm that is called arithmetic coding, and then you can show that it is the complexity is linear. Okay, so basically, I will now move to the second lecture that will be shorter. You have all the basics in order to understand. So you know that we need to compress, but the question is, how can we now compress data in the context of DNA-based data storage? Before I move to that, do you have any question? Okay, everything is clear. Okay, good. So encoding in the context of DNA-based data storage. So this is the scheme. We have to encode before synthesis, sequencing, and decoding. Okay. What are the specificities that we encounter in encoding in this context? Is that the sequences, so there are some constraints that the encoding has to satisfy for a DNA sequence. Well, that's a good. Yeah. So what are these constraints? You know that we cannot synthesize long sequences, so we can only do short length sequences. And yeah, that's where we have a problem, because all the theories that I showed you before, it was when n goes to infinity. Bon. Okay. So we have a first problem. Second problem, no homopolymers. So we should avoid the repetition of the same nucleotide. mostly. So well, we had courses on that, but so because so you know that the type, yeah, we've seen all this. I mean, the type of errors that you can have, it can be either substitution, which are classical in information theory. These problems are solved, but for deletion and insertion, it's not non-classical. And the problem is that you lose here a synchronization. So why, if you avoid, what is the problem with homopolymers? It's a problem of clock. So imagine, so imagine that you have your sequence that comes here, and you're, okay. And then you have A that is transmitted, so you have a homopolymer. And then you have your read clock that comes, and in fact, it's very difficult to make a clock that has exactly so that's a true problem, and to have a clock, to make clocks that are perfect. And maybe your clock here has is a little bit different from the one that creates your sequence. So what happens here is the two clocks are different, is that when you have the same repetition of the data, you will always read the same signal, okay? And there is no way for you to recognize that here the two clocks are not synchronized. On the contrary, if you had something that is different, here I make a T, I make a C, etc., the signal that you will have here, you have a transition here. Okay, another transition here and another transition here. And this transition helps you to resynchronize the clocks, okay? So not having, if you don't have this transition, if you have a repetition of the same symbol, the two clocks cannot resynchronize. So this is a problem, and this is the reason why we would like to avoid these homopolymers. So there are other problems. The secondary structure, so imagine that you have the repetition of a pattern, so it's not exactly the same repetition. So you have the reverse and the complement, and if this occurs, then the braid will fold, and and then you will have problem to be able to sequence the data. Okay, and then the last constraint is that you would like to have a GC and AT content that are quite balanced. So first, well, I mean, this is my understanding, and maybe if you, we have specialists here in the field, but you can correct me. But this is my understanding. You would like to have GC that is quite high. It's for stability, so I understood that the GC molecules are bigger, so it's better. But you don't want it to be too high, because since they are more stable, you have more chance or risk to have this kind of hairpin, okay? Bon, okay, so we have to do constrained compression, and how can we do that? So I will go to the first constraint, how to do short lengths. Well, this is something that has been done in communication for a long time. I mean, you split your data into, when you want to split your data in packets, in fact, it's a way the internet traffic works. I mean, you cut your data into packets and you send the packets, but in order to be able to put the two things together, you put an index in order to be able to identify the file, but also the part of the file that you are sending. So this is something that is commonly used, and yeah. Oh, that's a good way for me to advertise for a very nice chapter that has been written by Michel and Marc, and I took the picture from the chapter. Okay, so now how to deal with homopolymers. So here we will spend more time. It's a little bit more difficult. Okay, so yeah, there are different ways to deal with homopolymers. Either you can avoid them. You can put the constraint directly in your compression algorithm, or well, you can correct them. Then you will have to attend Serge's presentation this afternoon. He will explain you how to deal with, how to correct the errors, deletion and insertion errors that may occur. And or there is another way to do, is to, you do your compression, you can also add some protection, but you do a transcoding that will avoid this repetition. So, okay, so 2 that will be seen by Serge, and I will explain 1 and 3. So, do you want me to start with 1 or 3? So this. Well, anyway, I will start with 3 because because I prepare it that way. But I think it's better, it's easier to start with 3. But thank you for participating. It was. Okay, let's start with 3. Okay, so here, let's go back to theory. So what is a constraint transcoding? So I formalize the problem here. So I have a sequence of binary data that is coming in. There is a transcoder. The output of the transcoder will have symbols on a quaternary alphabet, ATCG. Okay? And the constraint is that the number of homopolymer is not the maximum number of homopolymer will be m. So this has been studied in computer science, and this is called the run. Okay, so the maximum run length is m. And what I would like to know is the optimal rate for a given m. Okay, so I write the problem. So just as we did before with the data compression. So I would like to have at the output of my transcoder a sequence with lengths and the average over all possible sequences has a length that is minimum. So I will compute I will not compute the length of the whole sequence, but I will divide it by k, the number of input symbols. Again, I compute, for us, it will be a number of nucleotides per bit, and I would like this to be as low as possible, under the constraint that the maximal run length is m. Okay? And well, I do information theory, so I will let k goes to infinity. Okay? So we can get intuition of what it means. So let's take at some particular case. Okay? If it is unconstrained, okay, when m goes to infinity, you know, there is no constraint, so you can, in one nucleotide, you can put 2 bits, right? And the optimal rate will be 1/2. But if m is not infinity, then the rate will be higher, and then you will get something that will be higher, greater than 1/2. But by how much? Let's compute that. But in fact, you know what is the optimal strategy. The optimal strategy would be to enumerate all possible constraint sequences and project onto this set. Okay? So let's do that. I will fix the length at the output of the transcoder, n. Okay? Now I will list all possible constraint quaternary sequences. Okay? So you know that it will be a subset of the set of all possible sequences. And then I will determine a binary set, okay, such that has exactly the same cardinality of this constraint set, and this will represent my input sequences that we'd like to encode, and we'll have then a one-to-one mapping between these input sequences and the constraint sequences. Okay? But the question is, how many bits can I put here? And if I can answer that, then I will have the optimal rate. Okay? Because the optimal rate for a given n will be the ratio between the length of the quaternary sequence, this is n, by a construction here, and then the length of the binary sequence. And then you know that was the second, I erase that, the second way to become a computer scientist. You know exactly when you have a set and you know the size of the set, you know exactly the number of bits you need in order to represent all the data of this ensemble. And this is the logarithm of base 2 of the cardinality of the ensemble that has to be, by construction, the same as this unconstrained constraint set. Okay. So if I can count the cardinality of this ensemble, I can compute the optimal rate. Let's compute it. In fact, there is a recursive formula that allows you to compute the size of the set. So it is recursive, so it means that you imagine you know the number of sequences that have the constraint m up to a length n minus 1. And now I would like to compute the number of sequences that have the same constraint but of length n. So let's imagine that you have a run of length 1 at the end. Okay? So how many such sequences do you have? Well, imagine that the previous, at n minus 1, it was an A. So you have 3 choices because the run has to be only 1. So these symbols have to be different. Okay? So how many choices do you have? You have 3 choices. The number of these sequences that ends with a run of length 1 is 3 times the number of sequences that are the same constraint and that are of length n minus 1. Okay, I can do one more step. If it is now, if the sequences ends with a run of length 2, you do exactly the same thing, right? It ends with an A. How many possibilities do you have? You have 3 possibilities because it has to be different from the previous symbol. And then it will be 3 times n, okay, n times the number of sequences here that have the same constraint and that are of length n minus 2. And then you can do that up to m. And what are the number of all such sequences? I mean, you only need to sum over all possibilities, and you get this very nice recursive formula. Good. Okay, so you remember, I have a recursive formula to compute it. Yeah. What is the initialization? So here we have to be careful because since you have a formula that goes over, so you take m terms before, you have to initialize enough, you need m initialization. But this is easy because if you have sequences of length smaller than the constraint, than m, yeah, how many such sequences can you have? These are unconstrained because they are smaller than the constraint. So it's easy to compute. The number of such sequences is always 4 to the power n. There is no constraint. So with this initialization and with this recurrence, you can compute iteratively the number of constrained sequences. And now you can wonder what is the growth of such a sequence. It's quite high. It's quite high. It grows exponentially with the length. And for this, you can get an intuition of that. Okay? So I will take, so imagine that the output alphabet is not 4, but 2. Okay? So it means that it's not a 3 that I will have here, but a 1. And imagine that, so, yeah, and imagine also that m equals 2. Okay, so what is the recursion that you get in that case? It will be n is n minus 1 plus n minus 2. And what is this sequence? Fibonacci sequence. Very good. This is a Fibonacci sequence. And you know that this grows, the number of such sequences grows exponentially. Yes, it grows, and here it's even more because m can be greater than 2, and the alphabet is also more than is a quaternary. Okay, so it grows very fast, which is good. Which is good. We would like that the constraint does not reduce too much the size of our possible sequences, and this is here what we show. So here I show the optimal rate that we can indeed compute. Okay, so we want the transcoding rate to be as low as possible, and this is a transcoding rate versus m. So this is a maximal run length, and you see. So that's quite interesting. Is that when already with m equals 4, then you can get to, you are very close to the unconstrained case. So maybe it's not a problem. It's not a problem. Well, but how do we do that? Because if we want to project on the set, so if you want to do the optimal encoding, then you will have a complexity that grows exponentially with the length. So we don't want to do that. So now we need to find practical scheme such that the complexity is not too high. So there is one by Goldman. So Goldman is a way to avoid run of length 2. So you can go up to 1. You cannot repeat a symbol. Okay. If I take my formula and I compute it, etc., what I get is that the optimal rate is 1 over log 2 of 3. Good. And Goldman works that way. So you represent your data with a ternary alphabet, and then you convert it into bases. So if the previous base was a T, then you can use only the remaining one. Okay, you have and since you encoded your data with a ternary alphabet, and then you know if it is a 0, you encode it with A, etc., etc. And in fact, if you compute the rate of such a schema, you can show you have in one nucleotide, you encode 1 ternary symbols. And what does it mean? So how many bits does it represent, a ternary symbol? It's log 2 of 3 bits, and therefore you have exactly the same optimal rate. So Goldman is optimal when the run length is limited, is 1. Okay? So I haven't seen the proof before, and it is in order, when I was preparing the talk, I just showed that, so I wanted to share this with you. So Goldman is optimal when m equals 1. Good. Now there are other schemes, another scheme by Blauwald. So here, the idea is that you take 8 bits and you will map it onto 5 nucleotides. And the goal is to avoid to have run lengths. So the maximum run length that you can have is 3. And how does it work? So you construct a code such that you have no run in the 3 first nucleotides, and you avoid that. You don't have to. So N4 and N5 have to be different. Okay. If you do that, well, you can compute the rate, so it is easy. So 5 nucleotides for 8 bits, so the rate is easy to compute, and you can show that the maximum run that you can have is when you have N5, N1, and N2 that are equal, and in that case, the maximal length, run length that you can have is 3. Well, you can show with this code that there is always you can construct a code such that you have always 2 possible sequences. So it means that when you encode with this scheme, for the same byte, so same 8 bits, you can have 2 sequences. So therefore, you have a kind of redundance. And this redundance is exploited in order to detect insertion and deletion. Okay? But you see that the rate is not so great. Huh? It's far from the bound. But remember that you can detect deletion and insertion. Okay, so there is another one. So this is a joint work with Sarah, who is here. We call this break sequence. So it was published this year. And the goal here is to allow runs of length up to m. So it's much more general than the previous schemes because you can do any mapping. And so the code design principle is very simple. So first you map always 2 bits onto 1 nucleotide, okay? And then if you notice that there are m identical nucleotides, you break the pattern and you map the next. So you map the next bit such that, on a nucleotide, such that it is different from the previous one. So then it's clear that you will break the run. There will no, yeah. But, okay, so good. Well, it's nice, but does it, can we do that? Does such a code exist? Yes, because when you encode a bit, you have two values to encode. And if you encode the new N3, the new nucleotides, you have three possible values because the only constraint that you have, it has to be different from the previous one. Okay, two values to encode, three possible values. It works. Yes, but it may not be so good in terms of rate, right? 2 for 3, you could encode more. So why not add another constraint? So when I encode N3, I will also impose that N4 is different from N3, okay? And doing so, I will push by 1 the start of a new run of a new homopolymer. It will not start in N3 with this constraint, but only in N4, okay? So, we constructed such a code. I will only show you the performance, and then you see that so you see here in yellow the rate that we can achieve with our code. So we have a code that is very simple. So you see, you just see, is it different from the previous one? And moreover, it works for any m. It's easy to make it. So you can also ask, yeah, but we added a constraint for rate efficiency. Does it help a lot? And the answer is yes, because if I have only the constraints that takes into account avoiding homopolymer, I will be here with a dash curve. So adding the new constraint in order to reduce the rate, it helps a lot. Okay, so we've been to how to transcode with a constraint. I would like to go now to other ways to do. So there is another way to do that's peer code that was presented yesterday. So the idea here is to introduce the constraint directly in the encoder. So here, this scheme, we can say that it is an end-to-end and it is non-binary. And it has many benefits. The first one is it is compatible with JPEG, and doing so, so it's my third point. So I said, yeah, direct quaternary encoding of the coefficients, but it's because there is this JPEG compression algorithm, it is robust to synchronization error, okay? And there is something that has to be said, is that this scheme was used as an anchor in the JPEG DNA standard, and this is an achievement, okay? So this is something that we have seen on Monday with Marc's talk, but I would like to go back to this figure in order to see what it means to use a JPEG algorithm and to be robust to noise. Imagine that you have a transcoding approach. So this is the approach that I've shown before, where the only goal is to remove some runs, to remove some runs, but some deletion can still occur. And if you do that, if you make a deletion at some point in the image, the rest of the image can be completely, everything is, you cannot decode anymore, and you have only something that is black. With the JPEG approach that we've seen in the previous slide, you see that you get much better results. You can still see the cat. So when the deletion appears, so there is one block that will be wrong. Then after, what you will see is a shift, okay, only, and there will be only a difference in there is a DC coefficient that is the mean of the image that is coded differentially. And that's the reason why you have, so the luminance is a little bit different. But you can still see the image. And there was another method that was proposed also by Marc's group, and it is based on vector quantization. And doing so, and when you have a deletion, then you will have a much better, I mean, the division will have an impact on the image that is very located, okay? Okay, so now I would like to go to GC content. So here I will like to, so this is my vision of the GC content problem. There are two approaches. Either you do it again optimally, you say that you have, you determine all possible constraint sequences and you project onto these sequences. Well, it will be very complex, but there is another approach. In fact, the practical schemes that we see in order to avoid homopolymers, we see that, okay, all these algorithms, they start from compressed data. And if the data are compressed, it means that the output is already, you already have a uniform distribution in year 0 and year 1. And when you do the mapping from binary to a quaternary alphabet, again, you will have something that is almost uniform. And the small perturbations that you add on the compressed data in order to satisfy homopolymer constraints, it will not change the statistics, okay? And what we have observed is that if you take many algorithms and you add this after compression, and if you add whatever the constraint, so whatever the way you implement the homopolymer constraints, they all satisfy this the constraint. So my vision of the thing is that this is not a problem. If you start from compressed data, you will always satisfy this balance between GC and AT content. Okay. So finally, so this is the last slide, and then I will summarize everything. So there is, just to say that there is a standard coming soon. It is JPEG DNA. The way it is done is a little bit different, but we've seen that in Marc's presentation, and I know that Michela will present it into more details on Friday. The idea is different. It's a trial and error process. I mean, you generate sequences, and if it does not satisfy the constraint, then you just remove it and you try to encode again. So, well, there are other ways to do. And now, okay, so here will be my take-home message about compression for DNA-based data storage. So, first things that we need to compress, okay, because we want to reduce synthesis cost and time. So we need to compress. And here, the main criterion will be compression rate. Then there are some specificities that we have to take into account to satisfy the biochemical constraint. And that's the reason why a new standard will come soon, so this is JPEG DNA. So the specificities that are taken into account up to now is a short length, no homopolymer, and GC and AT balanced content. So no secondary structure is not much taken into account. And here you see that the criterion is more about error resilience. And finally, so according to me, the main problems that we have to deal with, so it's how to evaluate in a fair way all these methods. The one that avoids the constraint, the ones that correct the constraint. And well, I think that here we have a lot of work to do, and that's how I would like to conclude my talk. Thank you.